Let's start correlation and regression analysis. During this lecture, we'll also go through some of the steps to handle data frame. So first of all, let's load the CSV file. Let me show you what is there in CSV file. Okay. So the CSV file contains three variables or three columns: reward behavior, transformation leadership, and employee behavior. And theoretically, let's say we want to see if transformation leadership has any impact on employee behavior. So this means transformation leadership becomes an independent variable, whereas employee behavior becomes a dependent variable. Okay, let's load the CSV file, but prior to that, we need to set a working directory. So the directory is where this file is stored. Okay, now load the CSV. Now if you want to see the structure of the data frame that we have, it is like this. Let's take out those columns on which we would like to do our analysis. Okay, so it is like this. So what is the structure of df1? If you see, now it contains only two columns. So as I said, we would try to create a regression model between a transformation leadership TL and employee behavior. Okay, if you want to know the number of rows in this data frame, so we have exactly 573 records. There may be some values which are blank, as you can see in the CSV file. There are multiple options of handling these blank values. One is, when you load this data frame, you can use this command as I have highlighted here, and you will have NAs where there are blanks. If you haven't done already, then we can do it like this. Okay, because our data frame is df1 now, because we have taken the relevant columns in this, so I'll use df1. Okay, so the blank values have been converted to NA in a data frame. Now if you want to see how many rows have NA, you can do this. You would again use df1 here and df1. Now this command would create another data frame named new underscore df with all rows which have NA somewhere in the columns. Okay, let's check that. Okay, so there were two rows, two records where NA was there. Now what can we do with this NA? Okay, for further analysis, we can omit this or remove these records. There are other options for dealing with NA values as well, but those are beyond the scope of this lecture as of now. I'm just removing that. Okay, now we have df1 with no NA values and two columns. Now let's find the correlation between TL and EV. As we looked earlier, we need to load a library for correlation analysis. Please note that there may be multiple libraries which may provide correlation function, but I am using this library HMISC. The RCORR is a function which works on metrics. So I am converting data frame 1, which is our main data frame, into matrix and trying to find out the correlation. Okay, now if you just print it, it will show you the correlation. Okay, so here is the correlation. 0.38 is the correlation between EB and TL. The p-value shows it is significant. If you remember and if you know about the p-values, so p-values are something which helps us to decide our hypothesis, whether we need to accept a null or alternate hypothesis. In this case, the null hypothesis was there is no correlation between two variables, but we need to reject the null hypothesis in favor of alternate hypothesis, which says there is a significant correlation between these two variables because the p-value is less than 0.05. Let's go to the linear regression part now. So we already discussed that employee behavior is a dependent variable while transformation leadership is a independent variable. So let's create a linear regression model. This is the command to create it. Now you have a model. You type this command and you find the statistics or the details of this model like this. Now what you see here, this is the formula that has been called residuals and their statistics, like the minimum, first quartile, median, third quartile, and maximum coefficients. So this is intercept, this is transformation leadership variable. The basic thing that you need to see to find out to check your hypothesis, in this case the hypothesis was, if you see these two sentences, transformation leadership does not have any significant impact on employee behavior. Transformation leadership has a significant impact on employee behavior. Okay, so if you see here, the p-value for intercept and this variable TL is less than 0.05, and if you see here, these are the significant levels, because for p-value mostly we consider if it is less than 0.05, we need to accept alternate hypothesis, and this means that there is a significant relation. But in this case, it is less than 0.001, so it is highly significant. So looking at the p-value, we can reject null hypothesis in favor of alternate hypothesis, saying transformation leadership has a significant impact on employee behavior. In simple linear regression, the adjusted R-square value shows a percentage of variance explained by a dependent variable in independent variable. So in this case, our TL variable explains 13.93 percentage of variability in employee behavior. Okay, so this is the statistics that you can use in your research paper or thesis. So I have seen many scholars who just run the regression model based on the data they have. They don't check for the assumptions which are very much required for the validity of the regression model. Here are those assumptions on your screen. So the assumptions are as follows: linearity of data, normality of residuals, homogeneity of residual variance. This means that the variance among the residual is constant, and independence of residual error terms. That means there is no correlation between the residual error terms. Now some of these assumptions may be checked while plotting the linear model, while others may be tested by running some statistical tests. Some of these can be validated by using both the plots and the statistical tests. So let's move further and see how can these be validated. I'll try to show you both the ways of validating these assumptions through the plot creation and using the statistical tests. Now you have the model. Let's say plot model 1. So you see this plot here. This plot here validates our first assumption, which is linearity of the data. The relationship between the predictor and the outcome is assumed to be linear, and this plot shows it is almost linear. So this validates our first assumption. Let's move to plot number 2. There are 4 plots. Okay. Now what does this plot tell us? Okay. The residuals errors are assumed to be normally distributed. Okay. So if you see, these are the residuals and they follow almost a straight line. So we can safely assume that they follow a normal distribution. Let's plot the third graph now. Our third assumption is the residuals are assumed to have a constant variance. It's also called spread location plot. It shows whether residuals are equally spread along the ranges of predictors. So mostly if they are randomly spread across the line shown, it means that they have almost constant variance. Okay, and which satisfies our third assumption. This is the fourth plot. It has nothing to do with our fourth assumption, but this plot shows the outliers in our data and if they are influential enough to impact our analysis. Okay. We can also test these assumptions through various tests. So here are some tests. If we want to check the normality of residuals, let's get the residuals in a variable. Okay. SR is a list of residuals we create for our linear regression. Okay, and now let's check with Shapiro-Wilk test. This is a test to check the normality of any data. The null hypothesis of Shapiro-Wilk test is data is normal, but because the p-value is here is less than 0.05, we can assume that the data is not normal. For checking out the independence of residuals, which was our assumption 4, that they are independent, so there is no correlation between the residuals, we need to run Durbin-Watson test. Okay, so Durbin-Watson test is there in library CAR. We need to load the library car. Please remember that if this library is not there, you need to first install the package car. I showed you how to install the package. Now the library is loaded and you can run this test. So it's almost 0.05. The null hypothesis is that the correlation is 0, while the alternative hypothesis is correlation is not equal to 0. In this case, it is almost 0.054. It's more than 0.05. So we can assume that null hypothesis is acceptable and the correlation is 0. Now, one of the other assumption was to test homogeneity of residuals. That is, their variance should be almost equal. We can use Brush-Pagan test for the same. Again, for running this test, we need a library to be loaded. This is loaded now, and you can run on our model that we created, and you can see p-value is less than 0.05. In case of Brush-Pagan test, the null hypothesis says that the variances are equal, but because the p-value is less than 0.05, so that means the variance among residual is not equal and there is heteroscedasticity present in the model. So this is how we validate our assumptions. So we try to verify our assumptions by plotting the regression model as well as by using some statistical methods. Please note that if some of the assumptions are not met, there are various ways of transforming the data and having these assumptions met. But the same is out of scope for this lecture. See you again in our next session.